The first step in learning how to design a computer or how to architect a computer is to learn its various parts. That is the topic of this video. We have earlier come across this hierarchy of languages. At the very top of this hierarchy is algorithm, which is nothing but a specification in natural language or close to natural language using some symbols of how to solve a particular problem. Algorithm is then converted to a higher level language representation, which is concise, very structured, yet is human readable and understandable by humans. Higher level language gets converted to assembly language, which is nothing but a human readable representation of machine language. Machine language itself is hardly human readable because it's in terms of binary numbers, zeros and ones. Machine language is in turn implemented using digital logic, which operates using electrical signals. So this hierarchy of languages comes into play whenever a real world problem has to be solved using a computer. Now think and tell me which of these languages in this hierarchy are specific to machines and which of these are independent of the machines on which they run. Algorithms and higher level languages are typically designed to be machine independent. They are not dependent on whether you're running it on a PC, on an Intel PC or a MIPS processor and so on. The bottom three in this hierarchy are machine specific. In fact, the machine language and the assembly language in some sense define a particular machine. Each step of conversion in this hierarchy is done by a particular entity or person. Can you tell which is the entity which converts the algorithm to higher level language? This would be the programmer. Which is the entity which converts a higher level language representation to assembly language? This would be the compiler. Now, what is the name of the entity which converts assembly language to machine language? This would be the assembler. It's typically implemented in combination with the compiler. That is, the same software which implements the compiler also implements the assembler. Now, who converts machine language to digital logic? This would be the computer designer. Here is a specific example. We have an algorithm which says something about computing the sum, which is converted to C code, a portion of which is shown in this example, and that is in turn converted to assembly code, which in the case of the MIPS processor looks as shown in this slide. It gets converted to machine code, which is a sequence of zeros and ones in a particular pattern, and machine code is implemented by digital logic using gates and flip-flops and switches. Here is a test for you. Can you tell which of these steps of conversion is this course concerned about? We in this course are going to be concerned about not so much the conversion process itself, but how the instruction set, that is the machine code, is designed, as well as how the assembly language is designed. We will also be concerned about how the machine language is implemented using digital logic. We now have the context to talk about the von Neumann architecture for computers. Most computers today follow this particular architecture. In this architecture, a computer consists of a processor and memory which interact with one another. There is input which comes from somewhere into the computer system, and there is output which goes out of the computer somewhere. An important aspect of this von Neumann architecture is the stored program concept, which means that the program or instructions as well as data are stored in memory. The processor has the job of getting instructions from memory, and the instructions operate on the data which is also fetched from or stored to memory. In the previous example, there were two instructions which had this, two MIPS instructions, load word and store word, which interact with memory. Load word corresponds to fetching data from memory, and store word corresponds to storing data into memory. As I said, most computers today use the von Neumann architecture. An alternative to this architecture, which one can possibly consider, would probably involve a direct implementation, a hard-coded implementation of the program logic using digital logic. And this would not involve a stored program where instructions are fetched from memory, data fetched from and stored to memory. These may not be involved. and such a hard-coded implementation would be inflexible and you could not run different kinds of programs on the same computer. All of you have used computers. If you are watching this video, you are using a computer right now. What are the various components of a computer you can think of? In the von Neumann architecture, there are 5 abstract components of a computer. In fact, they were shown in the diagram in the previous slide. These are input, output, memory, and processor, which consists of 2 subcomponents, data path and control path. Input devices are those that provide input to the processor via the memory. Examples include the traditional keyboard and mouse, touch screen, and also input can come from the hard disk or the network. Output devices are those to which the output from the processor goes via the memory. Monitor is a traditional output device, and also disk and network are output devices as well. There are different kinds of memory which a processor can use. These we will learn in this course as part of the memory hierarchy. The processor itself consists of, as I said, the data path and the control path. The data path indicates the layout of the digital circuit, the wires on which data flows, and the control path refers to the control which determines which data flows where and when. An analogy can help in understanding the distinction between data path and control path. If you take the analogy of the railway network, the data path would be the set of railway lines which have been laid out across an area, and the control path would be the control signals, the traffic signals for determining which train goes on which railway line at which time. So those are the 5 abstract components of a computer. Many of these are not really seen if you open up a computer. So this picture here shows what you typically see when you open up a desktop computer. You can hardly see the processor or the CPU. You can in fact see only the large fan which is used for cooling the processor. You can see a whole host of input-output devices, CD, DVD, hard disk, and a whole lot of power cables as well as data connectors, data cables for carrying the data. And then there is the motherboard which houses all of these components. Here are 2 more pictures of the same computer. Here we can see an external modem card as well as empty PCI slots. PCI is a bus technology which we will learn in the later part of the course. In the right hand side picture here, we can see main memory chips or RAM, and there are also some empty slots in this particular computer for adding additional memory. Here is an IO device which you have probably not encountered, is magnetic tape, which is used for backup purposes. So what you typically see inside a computer when you open it up, a layman's view, is somewhat different from the 5 abstract components of a computer which we learned earlier. If you open a computer, you will see ICs, flat and black components. The processor you can probably see if you look under the fan. The main memory, cache memory you can see. The motherboard which houses all of these components and has various input-output interfaces and bus components. You can also see various secondary memory components for non-volatile storage, magnetic disks, CD, DVD drives, and perhaps tape drive, and so on. In this course, however, going forward, we will be concerned about the 5 abstract components, which are, as you recall, input, output, memory, and then the processor which has 2 subcomponents, which is data path and control path.